Hello again. This will be the probably final lecture of 2 on negative binary numbers. It makes a kind of important philosophical point somewhere near the end, but it also helps answer some lingering questions students have about binary numbers from class, and you also get to learn about the famous sign bit. So you will recall that we defined a negative number to be the thing you add to the positive number in order to make 0. So if we picked, say, 6, for example, 6 over here is 0, 1, 1, 0. And in this lecture, I'm going to be using 4-bit binary numbers because I can get them all on one board here pretty easily. So a plus 6 is 0, 1, 1, 0. And then in order to get the negative, I would complement it, flip the bits, and then add 1. So let's over here, let's flip. Is going to be 1, 0, 0, 1. And then plus 1, that'll be 1, 0, 1, 0. And this should be equal to minus 6. Okay, so let's try that. 1, 0, 1, 0. And then I can add these two. 0. 1 plus 1 is 2, which is 0 and 1 to carry. 1, 0 is 2, right? 1 plus 1 is 2, which is 0 and 1 to carry. 1 is 0 and 1 to carry. And I get this extra bit over here. And as we mentioned in the previous video, if we're dealing with only 4-bit numbers, there's only 4 bits, and that last one goes away. And as I mentioned, that's a hardware phenomenon. If you're doing these things on paper, you add 2 3-digit numbers and you get a 4-digit number. That's usual, right? But in the hardware, there's only so many bits, usually like 8 bits in a byte or 32 or 64 bits in a register, like that. Okay, so so that's a minus 6, okay? And again, we can show that we can use the same process to convert from minus 6 to plus 6. So 1, 0, 1, 0, we'll flip it. This was plus 6 to minus 6. Minus 6 to plus 6. We'll flip it. So we flip it, we got 0, 1, 0, 1. Okay. Plus 1 goes to 0, 1, 1, 0. And that's equal plus 6. Okay? So that operation of flipping and adding 1 to negate a number works whether or not whatever we started with. We started with 1. With a plus number, we get a minus. And we start with a minus number, we get plus. The next thing I want to look at is what happens when we have 0. We didn't consider the questions of what happens if we try to negate 0. Like, what does a minus 0 look like? Shall we try it? Let's try it. Oops. Let's try it with this eraser. So we'll have 0, 0, 0, 0. And we'll go plus 0 to minus 0, if we could say that. All right. So we flip it, we get we complement the zeros, we get 1s, right? Complement plus 1. If I add 1 to this, I get what? I get 0 out, right? Okay. Okay, so that's good, right? There is no such thing as plus 0 and minus 0. If I take 0 and I try to negate it, I get 0. That's what I wanted. Happiness, right? Okay? Okay. All right, so let's think about the number line. Now, using 4 bits and straight binary, we get to represent the numbers from 0 to 15. So I could draw a number line if I wanted, right? And then on here, I could put the numbers. One, right? That's 2. Okay. 3 is 0, 0, 1, 1. And we won't put them all on there, right? And finally we get 14. And 14 is what? And 15 is what? Okay? So we can think of the number line, let me get out of the way here, we can think of the number line as going from 0, 0, 0, 0 to 1, 1, 1, 1, and that's our number line, if you will, like that. What about the negative numbers? What does the negative number line look like? Okay. Well, let's try it. This is the positive number line. Positive numbers. Positive numbers number line, right? Let's try a negative numbers number line. Well, the easiest part is 0. Okay? That's just 0, 0, 0, 0. We've seen that. Okay. We know what 1 looks like, right? 0, 0, 0, 1. What's minus 1? Well, let's try it, okay? So here we have 0, 0, 0, 1, and we will flip, okay? Let's just do this over here. Complement it, it becomes, complement it, we get 1, 1, 1, 0. We add 1 to it, we get 1, 1, 1, 1, okay? Complement plus 1, so this should be equal to minus 1. We add them. 1 plus 1 is 0, 1 to carry, 0, 1 to carry, 0, 1 to carry, 0. And we get 1 here, which we can get rid of. Okay? So this is legitimately minus 1. 1, 1, 1, 1. Minus 1 was 1, 1, 1, 1. Okay, what does 2 look like? 2 is 0, 0, 1, 0, right? So let's calculate minus 2. 0, 0, 1, 0, we flip it, we get, so this is 2 goes to minus 2, flip it, we get 1, 1, 0, 1, we flip that, we get this, right? Plus 1, we get 1, 1, 1, 0. Does that work? 1, 1, 1, 0, 0, 0, 1, 0, plus 2, minus 2, add them up, 0, that's 2, that's 0 and 1 to carry, 0 and 1 to carry, 0 and 1 to carry, and there's that stuff over there, okay? So that's legitimately minus 2. Minus 2. Okay. We'll do minus 3 now, although you might be getting the pattern. Three was what? 0, 1, 1, 1. Minus 3, 0, 0, 1, 1, I'm sorry. 0, 0, 1, 1. Let's fix that up. Okay. Minus 3, so if we flip it, we complement it, we get 1, 1, 1, 0, 0. Okay. We add 1. There's 1, 1, 0, 1. Let's try adding 0, 0, 1, 1. 1, 0, 1. Minus 3. 1 plus 1 is 0 and 1 to carry. 0 and 1 to carry. 0 and 1 to carry. 0, 1 to carry, and we're done. So that was minus 2. Here's minus 3. Minus 3 is going to be, what did we get there? 1, 1, 0, 1. Okay. So if I wanted to draw a number line vertically like this one over here in binary, we'll start out with 0 in the middle. Okay. And here will be the increasing numbers. So, okay. So this is going to be increasing in this direction. All right. This was 1. And minus 1 was 1, 1, 1, 1. So if I want to put my numbers up there in green, that's going to be 0, 1, minus 1, right? Minus 2 was 1, 1, 1, 0. Right? Minus 3 was 1, 1, 0, 1. Plus 0, 0, 1, 0, 0, 0, 1, 1. Okay? So this is kind of what our number line looks like in binary. Putting them in order. So I can keep going. This will definitely be 7. Should be 7. Okay, so what's minus 7? Let's calculate it. This was, I'm sorry, supposed to be in green. So we had 0, 1, 1, 1. Complement. Complement, flip it. We get 1, 0, 0, 0. Plus 1, 1, 0, 0, 1. Let's try adding them up. Minus 7 was 1, 0, 0, 1. We add. 1 plus 0 is 0. 1 to carry, that's 2, right? That's 2 and 1 to carry. That's 2 and 1 to carry. That's 0 there. So that works. So we can go all the way up here at least to 7. And down here, minus 7 looks like 1, 0, 0, 1. I want to do that in whatever that orange thing was. No, the purple thing. Here it is. Okay. So going this way, I can go, minus 4, 5, 6. Minus 7. Fix this up. My apologies. Minus 7 was 1, 0, 0, 1. And 7 was like that. Okay? All right, we're done. We got plus 7 over here. We have minus 7 over here. get out of the way. Plus 7 on the bottom, minus 7 on top. And now I want you to think for a moment and realize that we have missed something. There were 16 4-bit binary numbers that go from 0 to 15. Don't think of these as numbers for a moment. Just think of counting how many different bit patterns we have. Just think of, we have 4 bits. Each bit can be on or off. Okay? So each bit can be on or off, 4 bits. We have 16 possible bit patterns. So over here, on the positive number line, we've used all the bit patterns from 0, 0, 0, 0 to 15, right? 1, 1, 1, 1. All the bit patterns are here for 4 bits. What about here? Well, zeros, these 8 bit patterns are here, right? Or we could think of it as 1 and minus 1 as 2-bit patterns, 2 and minus 2, that makes 4, 6 bit patterns, 4 and minus 4 makes 8-bit patterns. 7 to minus 7, we're up to 14-bit patterns, and then the 0 makes 15. So if I think of the patterns of 4 bits, I've used 15 of them on this number line over here, from minus 7 to plus 7 with the 0 in the middle. Got it? What's the missing bit pattern? And well, the missing bit pattern is this one over here. It's 8. Well, let's put 8 in. Okay, let's compute minus 8. We'll complement, flip, 0, 1, 1, 1, plus 1. We add 1 to this, 0, 1, 1, 1, we get 1, 0, 0, 0, right? 1 carry, 1 carry, 1 carry, and then 1, 0, 0, 0. Okay, let's see if this works. Add them up, 0, 0, 0, 1 plus 1 is 1 to carry. And it works. Plus 8 and minus 8 produce 0, right? At this point, you're saying, wait a second, I forgot to notice something. I forgot to notice that plus 8 and minus 8 are the same bit pattern. Just like plus 0 and minus 0 were the same, right? Oh. Well, we can see why this happens. I have exactly 16 bit patterns, right? Plus 7 and minus 7, for every number, non-zero number, I get 2 of them. Okay, that's 14 there. Then there's a 0 makes 15. I'm left with only 1 bit pattern left, and I need 2 more numbers, plus 8 and minus 8. And this scheme just happens to give the same bit pattern for plus 8 and minus 8. Well, clearly that's not going to work, okay? We can't really have an ambiguous number. We got to pick one. Which one are we going to pick? Okay. What we're going to do is we're going to pick the minus 8. Okay. 1, 0, 0, 0 is going to be minus 8. And there won't be a plus 8. It's just asymmetrical. We got to live with it. Okay? Just like we don't have plus or minus 0, right? So there's only 1 0. We're going to have minus 8 and no plus 8. But, I mean, we ran out of 4-bit patterns. Okay. The reason we're going to do this is that you'll notice all of the left-hand bits are 1s for the negative numbers, and for the positive numbers, they're 0s. For this reason, that upper bit, the leftmost bit, is usually called the signed bit. If you're dealing with signed binary numbers, that leftmost bit tells you the sign. It's not like a minus sign. -1 was not the sign bit combined with a 1. Okay? -1 is a completely different bit patterns from +1. Here's 0, 0, 0, 1. Here's 1, 1, 1, 1. Right? -2 is a completely different bit pattern from +2. So it's not a sign bit in the same way that you're used to writing a minus sign in front of things. But it does reliably tell us whether the number is positive or negative. Okay. Now the next thing to understand is that when you take a number and move it around, and you'll remember that move instructions are a big thing in assembler, what happens if I have like an 8-bit number and I want to move it into a 16-bit register? So I have an 8-bit number that's negative, let's say it's a -3. So a -3, what was -3? That's a -3. And here's a +3. Okay, so if I add these up, I get my familiar 0. 1 + 1 is 2, 0 and 1 to carry, and then, okay. So, all right, so that's 8 bits. If I want to move this into a 16-bit register or a 16-bit location to get a 16-bit number out, I mean, it really is two different possibilities. One possibility is that I want to do something, or three different possibilities. One is that I want to move the 8-bit quantity into the 16-bit register and not touch the upper bits. So here's your 8-bit register. We'll have a 16-bit or longer. Let's put that down here. Okay. Okay. There's three possibilities. One possibility is to just move the 8 bits into the lower part and don't touch the rest. Okay. 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 Don't touch the upper 8 bits. Don't touch the left byte. Another possibility is to put zeros in the left byte. Okay? I'm taking this number, this 8-bit thing, I'm making it bigger. I could just say, all right, the extra bits will always be 0. So this is crud. Okay? And that will be put zeros. So this quantity is being moved to here, here, here. The last possibility is called sign extend. Sign extend takes whatever the sign bit was and propagates the sign bit. Okay. Sign extend. So if there was a 0 in the sign bit, that's a +3, then there'll be a 3 here. The sign bit of 0 goes here. If there's a -3 over here, the sign bit of 0 goes here. And then in 16 bits, this is still a -3. It works. You just extend the sign bit to make it longer. Okay? There's 3 different assembler instructions for this purpose. Okay? We can just move the byte. We can move sign extend. And we can move 0 extend. So all 3 possibilities are recognized and occur. Okay? So that's what you basically need to know about sign bits and negative numbers and number lines. Okay? Let's fix up our number line over here. So I lost my number line color. We can fix up our number line over here. We'll go to -8, which was 1, 0, 0, 0. Okay? So this is what the negative numbers number line looks like. Signed numbers. That's the signed numbers number line. Now I mentioned that there was a little bit of a philosophical lesson in this. And the philosophical lesson in this is that it's helpful to think of the numbers, the data that we're dealing with, as just bit patterns. And the interpretation you put on that bit pattern can vary. The same bit pattern over here, this is a -3. Over here, it's going to be what? It's going to be a +11. Got it? So 1101, excuse me, 110, it's going to be 13, I'm sorry. 1101 could be -3 or it could be 11, depending upon how you're thinking about it. That's how it works. Okay? And it's the same data in the same 4 bits of memory or register, but you could do some computation thinking of it as a negative number, and you'll get some instructions for that. Thinking of it as a positive number, you'll get some instructions for that. Okay? Or something else completely different. For example, if you have 8 bits in a register, and it's between 0 and 127 positive binary, then it's going to be an ASCII character. You could think of that byte, that 8-bit pattern, you could think of that 8-bit pattern as a character, a symbol. If you print it, what symbol will print? If you compute with it, what number will it be? It's the same byte. Okay? So that's the kind of philosophy. And this is a bit of philosophy that all assembler programmers know cold, because they do it a lot. Similarly, we have floating point numbers, which will be 32 or 64 bits. We could take that same 32 bits, we could think of it as a unsigned 32-bit binary number, or we could look at it and cross our eyes a little bit, and we managed to interpret it, that same 32 bits, as a floating point number with an exponent and an antecedent, a sign bit and all that stuff, okay? It doesn't matter. You know, the data is not inherently one thing or another. That one bit pattern could be one thing or another, depending upon how we compute with it. So that's the bit of philosophy that's in this. Okay, another bit of philosophy is be wary of the most negative number. So the most negative number is not the negative of the most positive number. And every now and then, that'll trip you up. Thank you.